Hello, welcome to our video abstract. My name is DiTommaso, and I'll be giving you an overview of the scientific and technical aspects of the Violet Space Weather Exploration mission. Violet is a part of the Canadian CubeSat project, a design-to-flight CubeSat program managed by the Canadian Space Agency. CubeSat New Brunswick is a collaboration between three institutions, MBCC St. John, Université de Moncton, and University of New Brunswick. Violet is a 2U CubeSat with a mass of 3.6 kilograms, and we're currently in the critical design phase with flat-sat development and engineering model manufacturing ramping up. Our tentative launch date is summer of 2022. The first science payload we'll go over today is the GNSS receiver for ionospheric and position studies, or GRIPS. Its mission is to provide insight into the behavior of Earth's ionosphere, providing real-time position, velocity, and time estimates, as well as total electron content. Acquisition of one or more GNSS constellation signals on two or more frequencies will be possible with this subsystem. And data will be recorded on the satellite and then downloaded to the ground station with 500 megabytes of data per orbit. And we're currently looking at one orbit of data per day. Next is our imaging payload, SASE, or the Spectral Airglow Structure Imager. SASE will be imaging the oxygen red line for airglow in the upper atmosphere at 630 nanometers. Since airglow is faint, a large aperture is required of 62 millimeters and a field of view of 30 degrees. SASE optics will utilize a Schmidt-Weissala reflector system, and further processing of the images will be done on ground to reduce blurring from motion of the satellite. The next experimental subsystem is the Hybrid Magnetic Attitude Control, or HMAC. Since PMAC was not sufficient to image the ionosphere across all latitudes, we had to go with a different option, making a hybrid system, including both active and passive magnetic components, including a permanent magnet, hysteresis rods, and air core magnetic torque coils. The magnetic dipoles created orthogonal to the permanent magnet by the torque coils will result in an angular offset, or beta angle, of the magnetic dipole of the satellite relative to the z-axis of the satellite. A Kalman filter will be utilized to accomplish sensor fusion of gyro, sun sensor, and magnetic field lookup table data to give us real-time attitude estimates. The final experimental subsystem is the S-band unit, or SBU. It's an in-house design with an omnidirectional radiation pattern, with microstrip dipoles being integrated, one on each of the 4 solar panels. Since the science payloads log large amounts of data, a high frequency band is needed, and our goal is up to 1 megabit per second data rate. And our transmit and receive frequencies are 2.405 and 2.433, but those are yet to be completely defined, as we have yet to be assigned those values by IARU. And finally, the bandwidth of the system is 2 megahertz. Thank you so much for tuning into this brief presentation. If you would like more information on our mission, please go to the website below. Thank you.